So before we get started today, I would like to quickly do a recap on the discussion that we had so far in this semester. So we looked at sorting algorithms initially, and later we looked at how to perform tree-based algorithms and also keep the tree balanced, right? So we looked at 2 to 3 tree and red black tree on keeping the tree balanced and perform an efficient search, insert, and delete. And later we looked at a variety of graph based algorithms. So we looked at how to traverse through a graph using BFS and DFS, and we picked up a problem in the shortest path algorithm. And later we looked at how to visit all the vertices in a graph using the minimum spanning tree. And we looked at the Dijkstra's algorithm. We also looked at the Prim's and Kruskal's algorithm when it comes to the MST, um, minimum spanning tree algorithms. And again, these are just a quick recap to what we had already learned in this semester. It's also important for us to take a minute and reflect on the different algorithms that we had learned um, so far. So now that we had talked about the graph based algorithm, um, we will shift our focus to a new problem in the CS, the string based algorithms. And we will simply pick one such problem in a string based algorithm known as the substring search problem. And we will look at a few algorithms that would let us solve that problem. We will also analyze the solution to such a problem and come up with their time complexity analysis. So to get started, let's look at the so-called substring search problem. Let us define the problem formally, and then we will look at an inefficient solution first, and we will also open up the discussion for uh, more performance-oriented approach later. So we are given with a string p, which is the input string, and we are also given with a pattern q, and we are required to find if the pattern q exists in p or not, right? So we need to find out such a existence exists. If it is existing, then we simply declare that as a hit. If it doesn't exist, then it's tagged as miss. So basically, there's two things, right? Hit or miss. If we could find such a string or such a pattern in that string, then it will be a hit, a miss otherwise. So this problem would be widely used in substrings. In a 101 class, you would have learned substrings in Java, right? So substring would allow us to go and find if a particular string, a substring exists, right? So we could find that using index of as well. And then there's contains. So these are like important keywords that's built-in functionality in a Java framework, right? So we all would have been using this um, in different times in our career, right? So every time we work with strings is an important data type, right? So we could find that all the files that has like unstructured data should be loaded initially as a string. The point here is how can we find if a substring exists inside a given string. And Java framework already supports that through some built-in functionalities, as we have said here, substrings, index of, and content and contains. So here we can see some examples, and the point here is that we would need to find a way to solve this problem rather than simply using the Java framework substrings. We would like to solve this problem using our own um, customized approach, right? So here you could see that in the first example, we are given with a bunch of characters in a string P, and then we are given with the Q, A, B, C, and we would like to find if Q is a subset of that P, right? So here it is the subset, Q is a subset of P, and hence it's a hit. As you can see, A, B, C is one particular character sequencing in that P. And if you look at the second example, again we have ABB, which is right here, right? So you can see ABB is again a subset. Q is a subset of that P, and again you declare that as a hit. If you look at the third bullet point here, we are looking for BCA, that's the pattern. We cannot find that pattern existing anywhere in the string, right? So when we say the pattern existence, we are going one at a time, a window by window, as we will see the example shortly. So we like to see if that particular pattern exists in that P. So here you can see Q is not a subset of P, and hence it's tagged as a miss. Okay, so how can we solve such a problem, right? So it's a very important problem here, the substring search problem. How can we solve it? Is there any algorithms that let us solve these? So there are a variety of algorithms. The first one being the brute force, which is the most inefficient one, which runs quadratic. And then you have Raven-Karp algorithm, which is again an efficient one, and it uses the technique called rolling hashing. Right? It uses rolling hashing. And Knuth-Morris-Pratt, also known as KMP algorithm, is again another efficient algorithm. You have Boy-Moore algorithm that would also solve the same problem. And again, when we are talking about that substring contains in Java framework, the framework would use one of these algorithm or maybe a customized algorithm from these, right? So it's still not so clear which algorithm that the Java framework is currently using. But they would use one of these popular algorithms or maybe a customized one, refining one of these algorithms. So today we will look at the brute force approach, but before that, why is this substring search problem important? So we are given with the patient's medical records. Let's say this is a string, and we want to find a particular patient's name, and let's tag this as the pattern. And here we could simply search using the substring search problem. We can search if the patient's name exists in that list of patient's medical records. Right? So in the second application would be, let's say we have a repository of resumes, and we like to find a candidate with a particular skill set, right? So that's like us saying that we want to search through a bunch of words in those documents, which is again here the resumes, so that we can find that candidate who would have a particular skill set, and that will help a hiring process, right? And we could also look up phone number inside contacts data set. Let's say we have a huge data set for a particular company for all their contacts. We could look up a phone number in that context data set using again the substring search problem. So when we had talked about the substring search problem different approach, there is also the regex matching approach. that many of us would be familiar with, right? So regex matching is again the regular expression matching, and that is again one of the approach that one could use when it comes to solving the substring search problem. But the idea here is that we want to make sure we take into account a particular algorithm that would let us solve this problem in a most time efficient way, right? So we are hoping that we could solve this problem in a linear big of n time, right? So that's our hope here, is that we would like to solve this problem in a linear time. So let's look at the brute force algorithm initially. Brute force say that extract substrings m of size q in P one at a time, right? So we take P, we take substrings M of size Q from that P, and we are going to compare that M and Q. And remember, P and Q are given to us, right? So P and Q is given to us. And here when we say size Q, we're simply meaning the length of Q, right? Length of Q. And then once we compare it character by character, one at a time, then we return hit if all characters match, return miss otherwise. Right? So we go through all the different windows in that P, which is the input string, and we try to find if that pattern exists. So let's pick one example. Let's say that we are given with a P right here, which is the string that has characters A, B, A, B, B, A, and then you have B again, A, B, C, right? So it's a bunch of characters. And well, it's worth noting that a string is nothing but an array of characters, right? So you should have learned that in a 101 class, that a string is going to be a bunch of characters inside it, which is again an array of characters. And then we are given with Q, which is the pattern, and we want to find if ABC exists. Matter of fact, it actually exists, ABC. And keep in mind, ABC should be ordered in the sequence that is given in Q, right? So we are looking for ABC. We are not looking for B, A, C, or C, A, B. We are not looking for different combinations. We are looking for the actual sequencing of ABC in that string, right? So that's the substring search problem. So the brute force approach here is we start with the first character, and then we set a window here, which is the size of that Q. Keep in mind, size of Q was 3, right? So the length of Q was 3. So we set the initial window size to 3, and then we extract that substring from P, and we are using that substring in M, right? So which is ABA, and we are comparing ABA with ABC, right? So it's not a match. You can see A matched, B matched, but A and C did not match. So it's a miss. All characters should match. So if it is a miss, then we go ahead and increment the window to the next size here, the window size. So you can see now the new window becomes BAA, and that's going to be your M. And you compare M and Q again. So B and A, already it doesn't match. If the first item doesn't match, then you don't need to do the search for the next items, right? It will be inefficient to do the search for all the items, right? Because if there's one item doesn't match, the whole thing doesn't match, right? So that's the idea, because we're looking for a perfect match where all the items in M and Q should match. So again, this is a miss. So we increment the size of the next window, which would be AAA, which is triple A. And again, you can see we do that comparison, and we find out at the second stage that the second item did not match. It's a miss. So we would increment it to AAB, and then again we find that it's a miss. So we are going to increment to ABB. As you can see, ABB and ABC. The third item is going to be the problematic one, right? So it didn't match. So in this case, we go through all the characters in M to find out that it's a miss. So once it's a miss, then again we increment the window, which is BBA. BBA is again a miss, so we increment it to BAB, which again is going to be a miss because we compare M and Q and find out that it's a miss. Matter of fact, this one we find out at the initial first iteration itself, right? So keep in mind, in your implementation, you should not run it 3 times in this case. If you find that one item doesn't match, then you will simply declare that as a miss and increment to the next window. So in this case, you have ABA, and again it's a miss. You increment it to BAB. BAB is also a miss. And then you have ABC, which is the final one, right? So ABC is your M, and A and A match, B and B match, C and C match. So you declare that as a hit, and you stop the processing. If you find, let us say, if you find such a hit somewhere right here, let's say you are looking for AAB, then you will stop right here. You will not do any further processing in the other other characters, right? Because we are looking for only one particular occurrence of that substring, and thereby if you find that, then you will simply say that we will stop the processing wherever we find that particular substring. So what is going on with the time complexity here? So you could see clearly that if we have a length P, then we need to run through all the characters in that P, right? So we start from here, A, and then we went through all the characters till this A here, right? So that's the lost point for us for our exploration. We started from A, and then we stopped right here. And that's what? 3 characters less than the size of P. So that's meaning P minus the size of Q, right? So that's how many times that we had iterated through that input string. But this Q here is going to be much smaller than P, so we can simply say that it is P, right? So the total running time is going to be P for just that input size. But then keep in mind, for each character, we did Q comparisons, right? So again, we can go back and look at this particular comparison. So for each of them here, right? So for each entry in that P, we did Q comparisons, right? So we had Q, the size of Q, the size of Q elements. So we did Q comparisons for each item in that input string. So if we are having P items, then it's going to be P times Q. That's how many comparisons that we are doing in total. So if we assume that the size of P is n and size of Q is n as well, right? So simply we could say that the worst case runtime is big O of n squared, and that's quadratic, right? But then there is a solution to this problem, that one could solve this problem in a linear time, right, rather than a quadratic. Think about it. Quadratic would be much more inefficient if we have a large data set with a big input string, but then we will use one of the efficient algorithms to solve this problem. So there's like a few tryout exercise for today. One is the brute force algorithm. Let's implement this algorithm and then conduct some experiments in this algorithm using different range of that data size, 1000, 2000, and so on. And again, in your implementation, you could randomize the input string and choose the same pattern and conduct the experiments, right? So once you had completed your solution, you should push your code. You can program it in any language of your choice to the GitHub repo that I would be sharing shortly. The next step for us is we will look at a linear solution to this problem in Rabin-Corp and KMP. If time permits, we will look both. If not, we will look at one of those. And Sedgwick 5.3 is our reading assignment for today. And if there are any questions, feel free to ask in our Slack page. Okay, thank you.